talk about the principle of conservation of energy. This law is one of the most important equations in engineering because it has so many applications. It can be represented by this equation. This principle states that the change in energy of a system is due to the sum of all energy transfers across the system's boundary. Let's expand each term of this equation and learn more about how we might understand it. Now, you might see this represented differently in different textbooks. But K here represents the kinetic energy associated with the change in speed. U represents the change in potential energy commonly associated with gravitational and elastic potential energy. And the E internal subscript represents the internal energy, which is commonly associated with dissipative forces like friction. What about the second term? Let's take a look. The first term here is the work acting on a system. That will cause the point of application to displace. The next term is the heat transfer, which is the energy transferred due to heat. These four T's each represent four other different forms of energy transfers. MW stands for mechanical waves, which can be thought of as sound or even ocean waves, for example. MT is commonly mass transfer. ER stands for electromagnetic radiation, such as a microwave oven or a light bulb warming you up. And then lastly is electrical transmission, which you could think of as the power being delivered to your hair dryer, the energy the hair dryer gains from that electrical transmission. Let's take a look at our expanded equation. This long equation is the expanded form of our initial equation and represents the principle of conservation of energy. It might seem like this is a long equation to remember, and it is, but with this single equation, you're going to be able to derive many other fundamental equations that are taught in a variety of different courses, such as thermodynamics, fluid mechanics, and many others, if you're in different domains of study. Let's take a look at a couple of quick examples. A block of mass m is pulled with a constant force of F over a distance d. The surface the block slides on is smooth. Find the final velocity of the block. So let's start off with our equation. I'm going to go up here and copy it. Now let's consider what we should do to move forward. Looks like we missed a t there. All right. So to use this equation, we consider each term and whether or not it's relevant to the given physical situation. Kinetic energy is definitely relevant in this situation. There is a change in speed, so we're going to be considering that. There's no change in potential energy because the block isn't changing height. There's no change in internal energy as well because when we're considering friction as the primary dissipative force, we know it's not relevant because the surface is smooth. There is work being done because the point of application of the force is moving the block. So we'll leave that one. There's no heat transfer because the problem doesn't mention anything about that. And it also doesn't mention anything about mechanical waves, mass transfer, electromagnetic radiation, or electrical transmission. So we can assume, those are 0 as well. So what are we left with? Well, we can see that the change in energy is equal to the work. By knowing the value of the force, the initial speed, and the distance, we can now easily calculate the final speed. Change in kinetic energy is a half times m times final velocity squared minus half times m times the initial velocity squared. And the work is characterized by the force F times the distance d. Well, we know that our initial velocity is 0, so we can cancel this term out. And now all we have is v and a bunch of known values. So we can solve for v. We multiply both sides by 2 over m and take the square root. Get that v is equal to 2fd divided by m in a square root. And let's move on to another quick example. A piston compresses a gas in a chamber with a constant force, F. The piston is at rest at points A and B. There is a large temperature difference between the room and the chamber. Characterize the system using the principle of conservation of energy. All right, once again, let's start with our equation. Our amazing principle. So in this case, there's no change in kinetic energy because it tells us that it starts and stops at rest. There's also a very small amount of mass in the system as we've defined it, which is just the gas. So we're going to assume that the change in potential energy is negligible or 0. Now there is going to be a change in internal energy. There is work being done on the piston, or on the gas by the piston, so we have that one. We also know that there's a large temperature difference between the room and the chamber. So we don't know what direction that goes because the problem doesn't tell us. But there is some heat transfer going on here. And similarly to the first problem, there is no mention of any of these terms, these other t terms. So we'll give that a long cross out. Now, what are we left with? Amazingly, though you might not know it at first sight, but this equation that we have just derived is the first law of thermodynamics, and it has been derived simply by knowing the law of conservation of energy. That's pretty amazing. First law of thermo. Now I hope you can see that applying the use of this equation is vastly powerful, and you're able to apply it to a wide variety of situations to help you understand and navigate physical phenomena. Thanks for watching. If you like this video, please like and subscribe and comment with any questions you have. Until next time.